This is going to be our first look at optimizing scalar-valued functions of multiple variables. So imagine that f is a scalar-valued function of multiple variables. Its domain A, which is a subset of Rn. In the past, we've always thought of that as open. It won't necessarily be open when we talk about optimization because we want to be able to consider what happens on the boundary of the domain. But what we will assume is that our function f is class C2 on A. So it is twice continuously differentiable on its domain. The first question for us to answer is, where do the extreme values of f occur? So for that, we're looking for, say, peaks and valleys, like in this particular picture. So here I have a function which I wrote in MATLAB. It looks a little bit like the MATLAB peaks function, but it's not. And the domain A was actually a closed disk in the xy plane. After I graphed this, I identified here two local maxima and two local minima. We are going to just talk about local maxes and mins in this particular lesson. So while this is the absolute maximum for this function and this is the absolute minimum, we won't distinguish between this and this, nor this and this. We also won't do things like look around the boundary in this particular lesson. So it's always possible that if you have, say, a nice compact domain, that your function will take its extreme values, its absolute max or min, on the boundary, and that won't be something that's necessarily easy to identify as a critical point. That's not what we're going to do in this lesson. We're just going to look for this, 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 and this. Okay, so how do we do that? Let me first write down a formula to describe the rate of change of f in any direction indicated by unit vector u. So recall, the formula I'm going to write down is valid for differentiable functions where our function is C2, so it's differentiable. I just want to make sure you remember that there is a hypothesis on this formula. For any unit vector u, indicating a sense of direction that you could move in the domain away from a given point P, the directional derivative of f at some point P in the domain, so perhaps the point P that mapped to this peak up here, in the direction of u. So what is the instantaneous rate of change of f if we're at P and we walk in the direction of u? Since f is differentiable, this can be computed by taking the gradient of f at P and dotting it with that sense of direction. Let me pause for just a second and think of what must be true about this dot product if we're at any of these 4 points. So just make a conjecture where I'm going with this. It should remind you of the first derivative test from single variable calculus, but this will lead to our way of detecting critical points in the domain. When we learned this formula earlier, we talked about the fact that this tells you that f has a max instantaneous rate of change and a min instantaneous rate of change, and also in what directions those would have to occur. So in particular, if the gradient of f at P is not 0, so let's imagine that for a moment, the gradient is not 0, then if you were a unit length vector which was parallel to the gradient and pointing in the same sense of direction, this dot product would be a positive number. In fact, it would be the length of the gradient, which would not be 0. That tells us that from P, there is a way to move which would indicate that your function goes up. On the other hand, if you were a unit length vector pointing in the opposite direction, so like negative the gradient divided by its own length, this would be a negative number. It would be -1 times the length of the gradient, telling us that from P, there would be a way to move down. So at P, we could detect both a way to increase and a way to decrease our function. Comparing that to just this picture of this function that we have here, we realize that if we are at a local max, then you can go down, but you cannot go up. So we cannot have a positive directional derivative at either of these 2 points. Similarly, down here at these local minima, you can go up, but you cannot go down. So there cannot be a sense of direction that tells us that our function goes lower if you walk in that direction. However, if the gradient is not 0, there's always a way to go up and always a way to go down, which tells us that, if we cannot go down and we cannot go up, it must be the case that the gradient is actually 0. And that is our test to find critical points. I'm going to call them CPs. Since we are only looking at nice C2 functions, we won't have any places where the gradient is undefined. So if this is reminding you of the first derivative test where you look for places where f prime is 0 or undefined, we are only going to be in that first situation. So our generalization of the idea that f prime is 0 is the gradient of f is 0. I've given you an explanation of that principle through the lens of the directional derivative. But if you look at this graphic, we are looking for places where the tangent plane would be flat, right? So it's like if you have a flat tangent plane, what would be the orthogonal sense of direction? It would be like this or straight down. And there's a way to compute this orthogonal vector. You can do this by taking, say, z equals f of x and y, moving the f over to have h of x, y, and z is z minus f of x and y, and recognizing that this would be perpendicular to this level set. Anyway, I'm not going to go into the details. That's why I'm saying this very quickly. But you can work out that this this orthogonal vector would be negative the gradient of f at p. Sorry, this should be gradient of f at p, comma 1. Or it could be gradient of f at p comma -1. This is the orthogonal sense of direction. That's in general. So if our vector points straight up like it does in this graphic, that must mean that the first in coordinates are 0 followed by a 1. So here this would look like 0, 0, 1. The gradient would have 2 entries. So that's a kind of more geometric tangent plane way to get to this principle that the gradient of f will be 0 at its critical points. That doesn't mean that whenever the gradient of f is 0, we must be having a local maxima or minima. In particular, for saddles, like if I just draw the one-dimensional example, something like f of x equals x cubed, you have a horizontal tangent line here, but it's not a local min or max. So of course, anytime you have a critical point, the gradient will be 0. But when the gradient is 0, it doesn't necessarily mean that you've actually reached one of these extreme values. For the rest of this lesson, the point P in the domain will be a critical point for the function f. A moment ago, I had that picture up here and I said the critical points happen when the tangent plane is flat. Another way to see that using the first order Taylor polynomial, I think this is even nicer, is if you look at the first order Taylor polynomial, so here I have second order, but forget that term for a moment. It will be flat. It will correspond to having a flat tangent line or flat tangent plane if it's only actually the 0th order term. So it's like saying y equals constant or z equals constant. That's going to give us that flat tangent approximation, which means this first order component must vanish, and therefore the gradient of f at p is 0. So that's just another way to get to our first derivative test looking for critical points. Since the gradient of f at p is 0, let's just forget about that middle term. Our second order Taylor polynomial is this 0th order term plus the second order term. 1 over 2 factorial, I've written that as a half, and then we have the Hessian of f at p. Since f is C2, that will be a symmetric matrix acting on the pair of vectors x minus p, x minus p. So when we talked about the Hessian, we know that that's a bilinear form acting on a pair of vectors via like a triple product. And f of p is a number. This is some quadratic behavior. So if we want to understand the shape of our function around a critical point, so whether it's maybe bending down or bending up or perhaps a saddle, it could even have other behaviors we haven't seen yet. Like if you imagine a parabola kind of stretched out, it could be a non-strict max, meaning you've got we'll see a picture of this later, but you know, every point along this ridge up here is a non-strict max. So that's another kind of bending behavior that we don't really have in Calc 1 or single variable calculus. If we want to understand how our function bends around its critical points, leading us to understand if we are at an extreme point or not, we want to understand this action here. So what is this telling us about the shape of our function at P? In order to do that, I want to take a little detour into linear algebra. So let's have Q of U be what's called a quadratic form. And I'm going to define it as the key part of this action. So forget about the 1 over 2. That's just a scaling factor. It's the Hessian matrix HF at P acting on U comma U. The reason I did that is just to translate the action to the origin. So when x equals P, that's like U equals 0. So you can imagine that u equals 0 is like centering this quadratic form at the origin, and then we're looking at how it behaves around the origin. If we can understand this, then we can translate it back to our actual T2 as it's written. Now, I haven't actually said specifically what a quadratic form is. Let me do so. So if you look at these 3 examples, they illustrate what a quadratic form does. It takes a vector and returns you a scalar where each of the components, like if you look at each of these terms, they are all quadratic order in the variables. So no constants, no first degree, no third degree. Everything here is like a degree 2 expression. So this quadratic form that we've created here based on our Hessian is going to tell us the behavior of f, which means I want to take a few minutes and kind of throw a bunch of theorems at you about quadratic forms. The first one is that any quadratic forms, like the three that we are looking at, can be written in terms of a symmetric matrix. We are going to establish this not only because our Hessian is symmetric, but because then we can analyze symmetric matrices using our knowledge of linear algebra. Okay, so this theorem, you can prove it in coordinates, but I think if I just do these three examples, it's pretty clear why it must be true. So if you look at this first one, we have just a scalar valued function on scalars, where q of u is u squared. If I want to write this as like this matrix triple product where the middle matrix is symmetric, what I would say is that this is the scalar u, which a scalar transposed is itself. So let me write u transpose times the 1 by 1 symmetric matrix, which just has a 1 in it, times u. Okay. For the second example, we have u1 squared plus 4u1 u2 plus 3u2 squared. And for this, I'll start with my row matrix. Just need to remember how to compute this matrix triple product to see why the theorem is true. So u1 meets u1 with the top left corner in this matrix. That's going to be 1. Similarly, u2 meets u2 with the bottom right coordinate, so that's going to be 3. And then we have two mixed expressions. So we have u1 times u2 and u2 times u1. Here we have 4 such mixed terms, so we're just going to split that in half. So 2 and 2. And that's really it. Take a moment to do this next one. For this final example, our quadratic form sends R3 to R. And when we put together the action of this quadratic form inside of this matrix triple product, we see that if I just look at the square terms, I get 2, 1, 0 down the main diagonal. And then for the mixed 2, 3 term, we just cut that in half, put 1.5 here and 1.5 here, and then 0 everywhere else, so that we get a symmetric 3 by 3 matrix encoding the action of this quadratic form. We are going to continue looking at quadratic forms in general before returning to the function that we're actually trying to analyze. And in particular, now we're going to focus on the symmetric matrix. The next thing we're going to do is just cover some vocabulary that we use to classify quadratic forms. Notice that a quadratic form is made out of a bunch of pairwise products. So if you plug 0 in for all the coordinates, it's going to send you to 0. So all quadratic forms are 0 at the origin. We classify them by what happens away from the origin. If it's the case that for any other input into your quadratic form, it's positive, so you have q of x is, or q of u, sorry, is greater than 0 as soon as you move away from the origin, then we say that's a positive definite quadratic form. And an example from R2 to R, all of these are like that, is just q of u1, u2 is the sum of their squares. So that's 0 if and only if we are at the origin, otherwise it's positive. It's possible instead that your quadratic form is non-negative away from the origin. So it could be positive, but it could also be 0. And to get that, all you have to do is just take off the plus u2 squared. So if u1 is 0, but u2 isn't, we are away from the origin, but this quadratic form is 0. However, if u1 is not 0, then this is positive. All right, so we have positive definite, positive semi-definite. Analogously, we have negative definite and negative semi-definite. So this just means strictly less than 0 away from the origin, and this is non-positive away from the origin. And then it's also possible that your quadratic form could go up and down as you move away from the origin. So here, u1 squared minus u2 squared. If u1 is 0 and u2 isn't, this is negative. Vice versa, it's positive. So this has mixed signs. And that covers every possible situation for a quadratic form. Let's now look at how we can figure this out. So for these functions, it's pretty clear because I picked nice illustrative functions for these vocabulary words. But if you had the matrix S and maybe it was n by n and you didn't have the ability to work out like so explicitly how it behaved, how could you detect this behavior? It turns out that we can classify a quadratic form if we can compute the eigenvalues of its associated n by n symmetric matrix S. Before I go through these statements, let me mention, hopefully this is a reminder from linear algebra, that if you have a symmetric matrix, it's known that the eigenvalues are real. So it makes sense to talk about them in terms of being positive and negative and quantities like that because they are never complex for a symmetric matrix. Okay, and then the theorem is basically that if all the eigenvalues are positive, it's positive definite. If they're non-negative, then it's positive semi-definite. If they're negative, it's negative definite. Non-positive is negative semi-definite. And if you have a mixture of eigenvalues, the corresponding quadratic form is indefinite. I will step aside so that you can read through these, and then we will come back in just a moment and I will do a little proof of this statement because I think it's kind of a nice proof. Our ability to classify a quadratic form using the eigenvalues of its associated symmetric matrix is due to a very elegant theorem from linear algebra called the spectral theorem. This is an if and only if statement about symmetric matrices, and it says that a matrix is symmetric if and only if it is what's called orthogonally diagonalizable. Since we already know that if we're studying a quadratic form, we're looking at a symmetric matrix, we're just interested in the forward simplification. I've written out here what it means to be orthogonally diagonalizable. It's a bit of a mouthful. If you've had linear algebra, hopefully this is familiar to you. If you haven't yet, please do stick with me through this, and I hope that when you take linear algebra, you will cover this theorem in depth. Let me give you a moment just to read through this because it's kind of a lot written down. I will come back and just organize this information about eigenvalues and orthonormal eigenvectors into matrices Q and D, and then we will talk about how to use this decomposition of S in order to prove this statement about classifying quadratic forms. All right, so we already had the special statement that a symmetric matrix has real eigenvalues. Let me organize those eigenvalues in a diagonal matrix D so that the main diagonal consists of the eigenvalues, which are not necessarily distinct, and some of them could be zero, but they are not complex. They're all real numbers, and then it's zero off this main diagonal. Now, a matrix does not always necessarily have n linearly independent eigenvectors to go along with its eigenvalues, but for a symmetric matrix, we do. So when I say here an orthonormal eigenbasis, I mean that for these eigenvalues, you can find n linearly independent eigenvectors so that S of, let me call them V, S of Vi, say this is the ith orthonormal member of the eigenbasis, is lambda I Vi. Okay, so we have S acting on an eigenvector, returning you back the ith eigenvalue times that eigenvector. We can find n linearly independent eigenvectors. That's already special. We can take each of those eigenvectors and make them unit length. That's not particularly special because you can always do that for a non-zero vector. But what's really, really important here is that your family of eigenvectors can be turned into an orthonormal basis. So normal means unit length. Ortho means mutually perpendicular, and that is special. So what we're going to do is create a matrix called Q so that the columns of Q correspond to the eigenvectors. In fact, they are the eigenvectors ordered so that they pair up with the eigenvalues. So if lambda 1 has eigenvector v1, that becomes our first column. And then lambda 2 is in the second position, so we'll put v2 here all the way through vn. With these two matrices, we can then actually rewrite S as the composition of three linear transformations from Rn to Rn. I don't want to go too into linear algebra here, but basically this is like convert into a new basis. The action of S is then similar to the action of this probably much simpler matrix, and then convert back to our original basis. So S being similar to this diagonal matrix means that we can write it as this product of three matrices Q, D, Q inverse. This form of this product is just a general way of expressing the idea that two matrices are similar, so S is similar to D. But since the new basis that we're talking about here is orthonormal, Q is what's called an orthogonal matrix. That's a very special kind of matrix, and it's one which is the easiest to invert because its inverse is actually just its transpose. So this product here, QDQ inverse, turns into QDQ transpose, and this is the key to the proof. Okay, everything I've said so far about what it means to say that S is orthogonally diagonalizable, which is preparing for the proof, which we are now going to start. There are a couple of different ways you could proceed with this proof, but they're probably related to what I'm about to do. You could work specifically with basis vectors. I'm just going to pick a random non-zero vector in Rn, so let x not equal to the zero vector be in Rn. I'm kind of laughing because where else would it be in this problem? We're working with an n by n matrix. Let me then act on X with the matrix Q and call the result Y. Let Y be Q times X. Q is invertible, which means that it only sends the origin to the origin. Since X is not zero, there's no way that this is zero. So Y is also non-zero. We find if I take my quadratic form and plug Y into it, that's going to be Y transpose S Y. I'll keep going to the right. That's going to be Y transpose. Now we bring in this version of S. So Q D Q transpose, and this is key, times Y. Okay, now I'll go down. This is just the product of 5 arrays, and matrix multiplication is associative, so let me regroup them. In particular here, notice that we have Y transpose Q. If you transpose this product of these first two arrays, transposing reverses their order and transposes them individually. So the transpose of this is Q transpose Y. Okay, so what I'm trying to say is this is equal to this. All right. And then D, and then Q transpose Y. Okay. So we have overall, this is Y transpose Q, D, Q transpose Y, and that's the same thing as Y transpose SY, which is Q of Y. But now notice that Q transpose Y is actually X, because if I wanted to isolate X in this equality, what I could do is multiply both sides from the left by Q transpose, and that is the inverse of Q. So on the left, we would have Q transpose of Y, and on the right, we would have Q transpose Q times X, but that first two, Q transpose Q, is just identity. So all that to say, Q transpose Y equals X. So it's like we've converted from one kind of quadratic form with this input to another kind of quadratic form with a related input, but the middle matrix is diagonal. If you expanded this out, so sorry about my board organization, I just have to prioritize space. If you thought about what this looked like, maybe I'll start to write it out in coordinates. We have x1 through xn as a row, and then we have lambda 1 through lambda n because D is the diagonal matrix of eigenvalues, and then x1 through xn. We can immediately compute this. It's not too hard to expand this because most of the entries in this matrix are 0. So we know x1 meets x1 with lambda 1, x2 meets x2 with lambda 2, xn meets xn with lambda n. So we have lambda 1 times x1 squared. Maybe I'll write that. Lambda 1 x1 squared plus lambda 2 x2 squared plus lambda n xn squared. Okay, I will read a little bit more down here in just a moment, but let me give you a chance to look at this and decide how much control this expression gives you over the possible values that Q takes. All right, hopefully you realized that what's really special about this result over here is that each of the components of X is squared. So none of these x1 squared, x2 squared, xn squared terms could ever be negative. That means that our ability to control the sign of this sum here really comes down to the eigenvalues. Let's talk through in detail the positive definite case. I think I don't have room to really write down 5 statements here, but let's see if we can just do some of this out loud. So imagine that our quadratic form little q was known to be positive definite. We're going to start there because it's actually an if and only if statement. So suppose first that we have a positive definite quadratic form. Then we know that this must be positive for all inputs which are not 0. Well, if I took the original vector x to be any of the standard basis vectors, say e1, so 1 in the first coordinate and 0 elsewhere, and then I got y by evaluating the orthogonal matrix on it, this result would actually just be lambda 1. So we would have lambda 1 times 1 plus the rest of them times 0. So by evaluating our quadratic form on like capital Q on each standard basis vector, we get back just the eigenvalues. We know by assumption that this must be positive, so all of our eigenvalues must be positive. Okay, so that's one direction of an if and only if statement done out loud. Let's go the other direction. Suppose that all of the eigenvalues were positive, then certainly this could never be negative because we have only positive and possibly 0 terms, so nothing here is negative. However, could it be 0? And it really comes down to looking at, like, if you have a positive number times something which could be 0, but a positive number times something positive, this is going to give us a positive contribution. So the only way that this sum could ever be 0 is if each of the x sub 1, x sub 2 through x sub n was itself 0, which means that we were at the origin. Because if this were 0, this would be 0, and we would have evaluated our quadratic form on 0. So if we are anywhere that's not the origin, at least one of these components won't be 0, which means we have the product of two positive numbers at least once, so the result is non-zero. So if all the eigenvalues are positive, the quadratic form is positive definite. Okay, I think I'll leave it there because ultimately what this video is supposed to be about is finding maxes and mins for functions, not quadratic forms. But if you want to, you can pause and take a moment to see if you can do sort of a similar balancing argument between, how to kind of mix together eigenvalues with these, like making a clever choice of x, perhaps. Okay, so what I'm going to do now is go back to the very beginning, looking at that picture where we had two local maxes and two local mins, and I want to try to tie our ability to classify quadratic forms to the Hessian to f. Now let's use our knowledge of quadratic forms to return to what we were talking about at the beginning, which is looking to better understand how to find these local maxes and mins for, say, a C2 function of n variables, which is scalar valued. We know that we're looking for critical points, places where the gradient is 0, so that our second order Taylor polynomial turns into a constant plus this quadratic piece built out of the Hessian. Since the Hessian matrix evaluated at P is symmetric, since f is C2, then that means to the Hessian we can associate the action of a quadratic form. So for the rest of this discussion, you want to think about the Hessian at P, HF at P, as playing the role of the matrix S in our study of a moment ago. Since it's a symmetric matrix, we know it has real eigenvalues. Go ahead and compute those eigenvalues. And then it's like, does that give you enough to then characterize f? Remember that f is not a quadratic form. F probably has other stuff going on that we have truncated or cut out of the picture when we restricted our attention to just T2. So the behavior of the Hessian might give you enough of an idea of the behavior of f, but it's not an exact perfect description, meaning that, again, f is not a quadratic form, so it's not equality, it's approximation. Okay, so I'm hinting at the idea that, the Hessian can be a good enough approximation, but not always. Let me just write down the statement, then I'll talk through how to think about it. Okay. If, as a symmetric matrix, the Hessian, I'll say, is positive definite. So you could think of the associated quadratic form as positive definite. So if it is positive definite, then that means that if you look at the associated quadratic form, then if this we're defining a quadratic form. As soon as you move away from the origin, you could only go up. And it turns out that that is good enough to know that, if you pass back to the original function f, not the quadratic form, but go back to the original function f, you are indeed looking at a local minimum. So I'll write then f has a local min at P. Uh, Positive definite, when I say positive definite for me, I think like positive, but keep in mind, it actually means minimum. So for me, the language is a little bit misleading when you just think about positive things as being kind of high. We're at a local minimum because if we move away from this, we only go up. That's true for the quadratic form, and also it tells us that f behaves the same way. And I'll kind of give you a working idea of why that's the case. I won't do a full proof here, but I will just say in a moment why that's the case. Negative definite, local max. So if the Hessian corresponds to a negative definite quadratic form, then f likewise has the same property that as you move away from it, the critical point, you only go down, and that's going to correspond to these local maxes. So here, the Hessian would be a negative definite matrix. Here, it would be a positive definite matrix. There's one more statement that we will use conclusively, and that is if the Hessian is indefinite, which to me sounds uncertain, but it's not. So indefinite, remember, means it has positive and negative eigenvalues. Then your function has a saddle. So if the Hessian is an indefinite matrix, it corresponds to an indefinite quadratic form, then that behavior does translate back to f, having the ability to go up and down as you move away from P. So that is a saddle. What I've left off here is semi-definite. So what if the Hessian is semi-positive definite, or actually it's positive semi-definite or negative semi-definite? And in those cases, you can kind of push it a little further, but I'm just going to stop this, like in this lecture, I'm just going to stop and say it's inconclusive. And let me give you an illustration of why. We know that the eigenvalues for our Hessian matrix are all real, so they fall somewhere on this number line. But 0 is really a boundary between two totally different regimes. So to the right of 0, we have, if all our eigenvalues are over there, areas where we go up. To the left, if our eigenvalues are negative, we have areas where we go down. Being right on 0, having a Hessian matrix with a 0 eigenvalue, places you just too close to two totally different conclusions. It's like this dividing line for a Hessian matrix, which is just approximating the function, is not conclusive because it's, if you think about taking this behavior and kind of imagining sending it back to f, how do you perturb it? Do you like maybe move it a little to the left, to the right, to 0? Either way, you would have different conclusions. So being on this demarcation, this boundary between two different behaviors is too fragile to make any conclusion with. On the other hand, if you imagine having a Hessian matrix, which is positive definite, if you graph the Hessian, which we will actually see examples of in just a moment, then you would graph something which was strictly increasing around your critical point. F is quite well approximated by the tangent. It's going to be really close to the values of the tangent around the critical point. So if those values shoot up, then f can't stay 0 or drop down. It's got to go up at least a little bit. So having a Hessian which only goes in one direction around a critical point is going to pull the function in that direction. Okay, so that's not a proof that this classification system works. I just want to give you an idea of why we use the Hessian and its eigenvalues to sometimes make conclusions about the critical points of f. With the methodology that we've built up, let's try it on a couple examples, and then at the end, I will wrap up with just some pictures of other behaviors that we might not have gotten a chance to see. So for this first example, we have f of x and y equals x squared minus 4x minus xy plus y squared plus 5y plus 7. We want to find and classify the critical points. Let me have you pause, and in just a few seconds, I will come back and I will have computed the gradient of this function, set it equal to 0 to see if I could find critical points. Hopefully our answers will agree. It turns out that there was only one critical point. So this is the gradient. It gives us a system of two equations for two unknowns. I made a ton of sign mistakes along the way, but I'm pretty sure I got to the right answer at the end. So what I did was I took this equation, doubled it to set up an elimination, wiped out the x variable, got y was -2, solved for x in this equation to get x was 5 plus 2y, giving me an x coordinate of 1 when y is -2, and that is the only critical point for this function. Okay, so we found our critical point. Now we just need to classify it. Again, let me have you do as much as you can. We haven't done this computation yet, but it's pretty routine once you have the methodology. So take your gradient, and from this, get the Hessian, plug in the critical point we have, and see if you can get the eigenvalues and make the right conclusion. All right, you should have gotten 1 and 3 for the eigenvalues of the Hessian matrix, telling us that the Hessian corresponds to a positive definite quadratic form, and therefore, going back to the function, we have at the point 1, -2, a local minimum. Okay, so just to check your work, here's the Hessian. It's actually a constant matrix. You can take the characteristic polynomial of this in order to compute the eigenvalues. That's like your traditional way of computing eigenvalues. But I like for a 2 by 2 matrix using the trace determinant form, especially if I'm just looking to understand the sign of the eigenvalues. So the trace, the sum of the diagonal 2 plus 2, is the sum of the eigenvalues. So lambda 1 plus lambda 2 is 4. And also the determinant is the product of the eigenvalues. So 4 minus 1 is 3. I've done here the work going from this pair of equations to the final answer, but I just want to point out that if lambda 1, lambda 2 is positive, that means both eigenvalues have the same sign. We're either doing positive times positive or negative times negative. And if their sum is positive, that must mean I added two positive numbers. So just from this, I could actually tell you that the Hessian corresponds to a positive definite quadratic form, and therefore the function had a local minimum. But if you wanted to get to the specific eigenvalues, I'll step aside now. And here's how I did it. You should have gotten the same thing. We will come back and do one more example where it's going to look a little different. Let me put up a picture of this function so that you can see the local min before we pick back up with our next example. Okay, let's run through this example, which is a cautionary tale. So here we have f of x and y is e to the x to the fourth plus y to the fourth. Let's just go ahead and compute the gradient together. So we are going to have e to the x to the fourth plus y to the fourth times 4x cubed by the chain rule. And then similarly for the y coordinate, e to the x to the fourth plus y to the fourth, 4y cubed. Okay. Exponential is always positive 4. So the only way that we're going to have a critical point is at the origin. So CP at 0, 0. If I want to compute the Hessian of this matrix, it's a little bit messy, but let me go ahead and tell you what the Hessian at the origin is. And you might be anticipating it. The reason you can't anticipate it is because all of these kind of polynomial terms in x and y are going to be present when we compute the Hessian, and they're going to be like we're not going to have any constants or anything like that. So when I put in 0, everything is going to vanish. Okay, so you're welcome to compute the Hessian in general on your own if you like, or using a computational tool. And then if you plug in the origin again, everything has at least an x or y in it, so everything goes away. This is the zero matrix. Its eigenvalues are both 0. If I created a quadratic form using this symmetric matrix, it would be the 0 map. I would say that means the outputs are both non-negative and non-positive. So this quadratic form should be called both positive semi-definite and negative semi-definite. Does that tell us anything about f? Not really, but just look at f. It's an exponential function. At the origin, we have e to the 0, which is 1. If we move away from the origin, we're only going to be raising e to something higher than 0. So it's going to be e to positive numbers as soon as we move away from the origin, so that's going to be higher than 1. So actually, if you just think about the behavior of this function, you get that it is a strict local minimum at the origin. Okay, so I wanted to give you this as kind of a cautionary tale. And sticking with this idea of like working with this kind of exponential function, let me just run through a bunch of, or like a handful of examples of this kind of function. And what I will do is I will graph for you the original function together with t2 so that you can see, the behavior around the critical point. I just want to wrap up by looking at functions kind of like the one that we just had. So this is a graph of f of x and y equals e to the x squared plus y squared. In each of these graphs, the original function is the more opaque surface, and the more transparent one is a graph of t2. So here, for one thing, if you have e to the x squared plus y squared, there's actually a trick to get the second order Taylor polynomial very quickly. Comes right out of the Taylor polynomial for e to the x, so it's 1 plus x squared plus y squared. Okay, our critical point is at the origin. To do the Hessian for this matrix, you get 2, 0, 0, 2. When you have a diagonal matrix, do not do a characteristic polynomial to compute the eigenvalues. They are literally these diagonal expressions. So the eigenvalues for this matrix are 2 and 2. This is a positive definite matrix, and we see that in the picture because we have a local minimum for our function. Okay, let's look at the next example. So here we have e to the negative x squared minus y squared. The Hessian is -2, -2, like this on the diagonal. So those are the eigenvalues. This is a negative definite quadratic form, where this is associated to a negative definite quadratic form. And as expected, we have a local max for our function. I like this picture compared to the first one because we see that just around the critical point, T2 is a really good approximation for F, but it's more obvious here that as soon as you start to move away from it, they really do diverge. Okay, our next example is e to the x squared minus y squared, for which the Hessian is 2, 0, 0, -2, diagonal matrix. So the eigenvalues we read right off the main diagonal, 2 and -2. It's indefinite, and notice here we do have a saddle. Okay, last two examples, we have 1 plus x squared for the t2 because this function is f of x and y equals just e to the x squared. That means that our Hessian is now 2, 0, 0, 0. This is positive semi-definite. And that does make sense here looking at the picture. So we have a way to go up and also a way to not go up, but that's kind of special happening here. So we have a non-strict local minimum. As I said, I do not want you to immediately go from positive semi-definite to assuming this kind of behavior happens, because in our previous example, we had positive semi-definite, or like example from a few minutes ago, positive semi-definite and positive negative. We had both of the semi-definite cases, and actually we had a strict local minimum. So again, I just want to throw that out there as a cautionary tale. Our final example in this family of pictures is 1 minus y squared for t2 because the function is f of x and y equals e to the negative y squared. And we have a negative semi-definite matrix, and we do actually have a non-strict local max. Okay, so that wraps up our look at how to use the Hessian matrix, and notably its eigenvalues, to classify critical points. Thank you for your attention.